So you can see my title here. It's a little bit soft for an engineer, you know. And part of that comes from me being a biomedical engineer and working with the human body. And it turns out that, you know, when you think of engineering and you think of simulation and modeling and all of these things, if you're a mechanical engineer, you know every nut and bolt in a car that you've designed because you designed it and you put it there. Now, when you work with the human body, as a biomedical engineer does, you approach it with some humility. And this is my sort of approach to sort of working with the human nervous system. So, you know, the human nervous system is interesting because, you know, it possibly defines, you know, who we are and what we are. Again, just to tell you, you know, there are two control systems in our body. One is our so-called humoral system, where our hormones control things. Those are really chronic and longer-term control systems. The other control system is really the nervous system, which basically creates who I am, my perceptions, as well as coordination of all my activities. And so it's a big deal to who I am. And unfortunately, there are many instances where, you know, things don't work quite as they should. And there's a list of disorders here, if you will, of the nervous system. And my research and those other researchers here in neuroengineering at Georgia Tech and in neuroscience basically work at trying to figure out how the nervous system works, or in some ways, as I'll show you today, how to modulate the nervous system so that it works the way we'd like it to work. Specifically, I'll talk about two areas. One is called neuroprosthetics, and Steve Potter will talk about it a little bit also later. And the last part, I'll talk about brain cancer. And so I know it sounds morbid, but hopefully you'll see what it is. So as important as the nervous system is, it turns out that the influence of technology in modulating the nervous system is very crude. You typically take, you know, pills that govern the absorption or desorption of some chemicals in our brain. But really, technology has not penetrated the modulation of the nervous system to the extent that it has penetrated, let's say, your cardiovascular system, where you can have stents and you can have balloons and you can have all of these things. Or in your orthopedics, where we have artificial hips and knees and all sorts of body parts. Now, largely that's because those interventions are sort of mechanical in nature, and we know how to deal with that. Whereas the functioning of the nervous system is a little bit different. It has connections and it has cells that talk to each other. And so modulating the nervous system is a little bit more complicated than changing the structure or the shape of some structure in our body, and hence the challenge. So today, and neuroengineering essentially is the discipline that helps us do that, help modulate the nervous system. I'll tell you two stories today. First, in the first part, I'll show you two examples of relative successes, if you will, of the implications of modulating the nervous system. And then I'll talk to you about our work with brain cancer and the role that technology might play. So the first example is sort of arguably one of the most successful interventions for modulating the nervous system, and that is to treat deafness in children. And this is the cochlear implant. So the way we hear is that, you know, sound falls on our eardrum, which vibrates, is connected to a series of bones that then go into a region called the cochlea, where different frequencies change hair cells that move depending on the location, that then connect to our nervous system. So in certain conditions, this system has gone awry, and so there's an implant which is basically like a pacemaker, except instead of a single lead, it has a long tube that coils into our cochlea. And each of this has connects and different levels of connectors that helps you stimulate the nervous system in different locations in the cochlea. And this has really revolutionized things in such a way that if you put it in early enough, children who would otherwise be deaf and not be able to speak because they're deaf are actually able to integrate into normal schools and things. Now, there is a little bit of controversy about this because there are many who are deaf who believe that it is as it is, that it is not a disability of any kind. And so setting that aside, this has been an amazing success story. Just to give you an idea about what this sounds like, the sound from a cochlear implant, I thought I'd play a sound. And this is crude, but still good enough to give speech to children and have them go to normal schools. And let me just play this.
This is an example of an 8-channel processor. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
So this is how. So this is an 8-channel processor. So there are 8 electrodes in the cochlea stimulating it, and this is the sound you would hear from a cochlear implant of this. But it is good enough for the child to learn how to speak and carry on a conversation on the phone and basically integrate into quote-unquote normal society. The other sort of dramatic illustration of technology comes from, again, an electrode being implanted in the brain, this time for Parkinson's disease. Now, in Parkinson's disease, many of you know, Michael J. Fox and Muhammad Ali. There's a region of our brain called the substantia nigra, very small deep in the brain, and hence this technique is called deep brain stimulation. And it turns out that until about 85% of this very small region of our brain dies due to some unknown etiology, we don't see the first symptoms, which are usually presented with tremor. Now, there are many aspects to Parkinson's disease besides the motor aspect, but that's the most obvious one. So one of the technologies that is actually revolutionizing the treatment of Parkinson's today has to do with a pacemaker implanted in a certain location of our brain to treat the disease. And I show you this video again to give you the power of technology to modulate and affect the quality of life of human beings.
It's based in the brain, I understand, kind of level with the top of the nose and the ear. And it is connected to a battery in my chest, in the skin in my chest here. And this is controlled. I can control the amount of the voltage going in. I can control the length of time that the pulses. And I can identify the number of times per second that it goes in. And I'll turn myself off.
So he's turning off the stimulator now. So he's trying very hard to control it, but he's going to turn it back on. So this I use to illustrate the sort of power that technology has to modulate our nervous system and to do it well. Now, if you look at brain cancer as another sort of challenging foe, and I call it a sort of old adversary and the reason we're motivated by this in my lab is that if you look at, there are many kinds of brain cancer. One of the most challenging parts is this form of cancer called glioblastoma multiforme. Now, unfortunately, if you look at the survival rates 5 years after, right, the survival rates have not changed from the 1960s, all right? And this is, we've had many, many interesting things happen in medicine, but for GBM, we're still looking for a solution. And the reason I would argue is that, and I'll tell you in 1 second why this particular form of cancer is particularly dangerous and tough to deal with. But also, mostly our approaches to solving it have been to try to find more and more toxic chemicals to kill it. And I'll tell you in 1 second why that's a problem. And the reason it's a problem is because brain tumors of this form are extraordinarily invasive. They start at some location in the brain and then do not ever stay there. And our first approach to brain tumors is always to try to resect them out surgically. Now, when you try to resect tumors out, when it is another organ, like the breast, for example, you can be radical about it and say, when in doubt, you take out more tissue, or you could resect the whole organ, right? In the brain, every millimeter is the difference between your ability to perhaps speak or walk or affect who you are. So you're very conservative about how much you can take out because you don't have the luxury of doing radical surgery in the brain, right? So, and with that coupled with the fact that you don't have an edge really, and you have this invasive tumor which is a moving target, you know, dumping more and more toxic chemicals here is not a good solution because you normally kill the other normal tissue that surrounds this invading fronts of the brain tumor. And hence the challenge and hence our inability to sort of move the needle since the 1960s with this disease. So we asked a simple hypothesis. What if we halted the spread of the brain cancer? Is there something intrinsically so bad about brain tumors that they're hard to kill? Or is it the fact that they tend to invade that make them so challenging? And if we had some means to stop them from invading, could we then turn them into any other cancer, and would they respond to our toxic chemicals that we already have that are capable of killing tumors? And in search of that, we had a collaboration with Jack Arbizer here at Emory, who's a sort of mad chemist who makes vials of different colors. My son loves his office because he's got plants and rocks and things, and he always comes away with gifts from Jack's office. And he's basically an MD, PhD from Harvard, brilliant guy. And he likes making new compounds for cancers. And so he gave us like 30 of these that we screened, and we found one. And so I won't go through the data. Essentially, we found one that halts brain tumors at a low enough dose that it can be a therapeutic, doesn't affect normal cells of the brain. And so that's what this data is showing you. On the left, it's a dose curve. And on the right, it's normal cells, astrocytes. And it doesn't affect astrocyte function, but it affects brain tumor cells and only their motility, not toxicity. So we screened for a drug that was not toxic, but just stopped them from moving. So, and we did that by growing little brain cells in a dish that invade, and you can add the chemical to screen for how this works, if you're wondering how we did that. So that's how we were able to screen many, many compounds without having to kill animals and such. So you can do this in vitro. So we then asked the question, well, could we give this drug? It turns out that the drug was a pretty bad drug because it stayed in circulation for just a few minutes. And for it to get to the cancer, you needed to stay in circulation for a long time. So we put it in little nanocarriers that are 100 nanometers in size. So 100 nanometers. So our hair is typically 25 microns, right? So a nanometer is really, really small. So you couldn't see them. You need an electron microscope to look at them. But these are little fat bubbles, if you will. They're made of lipids. And on the surface of these, we play a little trick. We bind polymers that love water, like polyethylene glycol. In fact, polyethylene glycol is in your ice cream in many places. It loves water. So what we do is when you coat a nanocarrier with this water-loving polymer, you make the body think that it is a bubble of water that's just flowing around your blood, so it tends to last longer in blood. The reason it's important to last longer in blood is that it turns out your brain tumors and any other tumor, as they grow, they want to make their own nutritive supply, so they make their own blood vessels. So in the process of making their own blood vessels, as they're growing, so they make the blood vessels leaky. So what happens is over here, so the tumor blood vessels are a little bit leaky because the blood vessels are still being formed. So if you have something in circulation for a long time, let's see if this is a movie, yeah. So if you have something in circulation a long time through the leaky blood vessels, the drug gets to the tumor. So by putting a drug inside this lipid or fat bubble that is coated with water-loving polymers, we made a nanocarrier, if you will, that changed the pharmacokinetics of this drug, which was useful but had no way of getting to the tumor. So this is where the engineering comes in with nanotechnology, where we took a drug that was good but had no way of getting it and packaged it in a way that it could get to the tumor. So when we did that, we had a remarkable result, and this is in rats from my lab. This is the work of Jenny Manson. So the tumor was put in over here and spreads to the other side, just as I showed you in the cartoon. Whereas in this case, the tumor basically stays on the side that we put the tumor in. When this is treated with our nanocarriers, when this is not treated, it spreads, goes on to the other side of the brain. Okay? But this enhanced survival by about 15% or so. It is statistically significant and such, but it didn't really change the world. But then remember our hypothesis. We asked, if we were able to halt the spread, and we were able to here, does it respond to conventional chemotherapy? And so, and this is just showing you a picture. So to help us analyze this, what we do is we put brain tumor cells into a rat that are coded for a green protein, so we can find the tumor tissue distinctly from the normal tissue, which is coded in red. So here you see the untreated brain tumor. There's lots of green invading the brain, whereas in the treated case, there's a little bit, but not as much, okay, at the bottom. And you can quantify that spread, and that's what the data on the right is showing you. So what we then asked is, well, if I'm able to stop the spread of tumor, can I give it conventional chemotherapy, and will it respond better? And this is the data. It's all lines and squiggles, but I'll show you how this data is read in 1 second. So on the y-axis here is the sort of survival. And each time you have an inflection point, you've lost one of the animals that has the brain tumor. So there are about 4 cases here where we give just the chemotherapy, just the nanocarrier which stops the spread, or in one case just empty fat bubbles, and in one case where we first halted the spread of tumors and then treated it with the chemotherapy. Okay? And what you see is the top line, which in my 12 years of doing research on brain tumor we had never seen before. And that is, we did not lose a single animal that was treated first to stop the spread and then with the chemotherapy. That was an existing chemotherapeutic drug. So we didn't invent a new drug to kill the tumor. We just made the tumor stop moving so that the drug could do what it needs to do. And in every other case, we did lose animals. So this is a pretty remarkable result. Just came out last week and hit the press a little bit. And it's actually very touching when something like this comes out. You get a lot of emails from parents and relatives about when this could be available clinically. But it is the first instance of a drug that can safely halt the spread of brain tumors using technology. I'll show you one other example, which is a slightly crazier idea, if you will. And that is, not all brain tumors, it turns out, lend themselves to chemotherapy or surgery, because some of them are in brainstem regions, where the brainstem is the part of your brain that helps us control breathing or autonomic functions. So if you have a brainstem tumor, it's actually very tough to operate. So I had this crazy idea one day to ask the question as the following. If tumors are so invasive, is there some way I can use that to my advantage? And the crazy idea was, if they want to move, and I understood how they moved, can I design a path for them to move along that I specify the direction in which they move? All right? And the idea conceptually is this. So I'll play the video so you can see what the idea is. The idea is this. If I have a tumor, you'll see it in red, inside the brain. I want to design a path. It turns out, and these are fibers that they move along white matter tracks, which are like fibers. So I want to design a path that, that basically is minimally inserted. So this is it. For now, we have a 10 micron path that the tumors are using the same mechanisms that they would use to invade in the normal brain, invade along, but they come out of the brain from some deep part. And they come to an area, to a gel that I designed to kill the tumor cells and only the tumor cells. So this is, instead of taking the drug to the tumor, can we make the tumor come to the drug? Because we know the tumor likes to invade. We know that it follows certain directions and certain rules when it invades. And if I understand that and translate that understanding into an engineering problem, now this is again a very typically engineering mindset, if you will, because this is not something a cancer biologist would think of. And so we have, in fact, there was a lot of skepticism in my own lab about, the craziness of this thought. But in fact, I see Jonathan here who's working on this project, and Anjana and a couple of others in the lab. And so we tested this out, and this is work from Anjana, who's now a professor. So what Anjana did was, in the first design, she engineered these nanofibers which had oriented filaments in them. It turns out when brain tumors invade, they use our axons, which are these long wires that are running around our brain connecting different parts. And so she noticed, and we know from literature that that's how brain tumors invade. So we made this film, and she made a round carrier which was smooth, which acted as its own sort of intrinsic control. So the idea is that if you stick this tube with a film in the middle, which is the cartoon depicted here, and at the end she made a gel that was toxic to the tumors. And the idea was, if I stick that front end into the tumor somehow, will the tumor invade along the fibers? Will it go on the smooth film, or will it go only on the fibers in the middle, because that controls for how it's moving? And will I kill the tumor cells? And the data below here in the green is showing you that when I just have an empty tube, I don't get to move the tumors out of the brain. And whereas at the bottom right here, you can see tumor cells moving along this fiber into the tube out of the brain. And in fact, they invade, again, the dark brown spots here is tumors dying in the gel that has the toxic chemical in it. But if you have a gel without the toxic chemical, they don't die. So you would just move the tumor but not kill it. All right? So this is the first demonstration that we know of moving a tumor from its primary location on its own volition, no suction, no anything, using characteristics that it would normally use to invade the brain, to come out of the brain to a region that we specified, right? So it's pretty exciting. So I'll end on this note. So I talked about this being technology to dance with nature, and I call it dance with nature, and it is soft because we don't understand how tumors work, how the brain works. It's like a black bog. We do something and we watch what happens, we do something again, and slowly we dance with nature. And that's what we're doing. And with that I'll end, and I want to thank many people who help us fund our research to make this happen. Thank you so much.